Hackers, have you ever wondered how two people can communicate in secret on the internet? Well, you might just say use symmetric encryption or AES, and you would be right, but how do they share the key with each other? You need a key to encrypt the key. Well, it turns out that's exactly what the Diffie Hellman protocol solves and is what we will cover today in theory and in code. I'm Rudy, you're on Block Hackers, let's get hacking. So Diffie-Hellman in theory is easiest understood using a color analogy. Alice and Bob want to talk to each other over the internet. They both agree on a shared color. Let's call it the generator. And in our case, let's use yellow. Alice and Bob both come up with a secret color at random that they never share with anybody else. They take the generator and mix it with their secret color. Alice mixes yellow and red to get orange, while Bob mixes yellow and blue to get green. Alice then sends her orange over to Bob, and Bob sends his green over to Alice. Notice they don't share their original secret colors. So far, the attacker has only seen yellow, green, and orange. Alice takes Bob's green and mixes in her secret red, which gives her a particular kind of brown. And then Bob takes Alice's orange and mixes in his secret blue, which gives him the same brown. And we know it's the same brown because in both cases, it's the color formed by mixing the generator yellow, Alice's red, and Bob's blue. So how does this work mathematically? Well, first, we get to take advantage of the following phenomenon. When you take a number b and you put it to the power of x and then in turn put that answer to the power of y, you actually get the same as b to the power of x times y. For example, 2 to the power of 3, then to the power of 4, is the same as 8 to the power of 4, which is the same as 2 to the power of 12, which is 4096. So let's start by agreeing and sharing a number g, a generator g. Alice then picks a random number a, and Bob picks a random number b. Alice then computes public a as g to the power of a, and Bob computes public b as g to the power of b. They then send these public values to each other. Alice can compute a shared secret by taking Bob's b and raising it to her secret a, and Bob can do the same. This results in both Alice and Bob holding the same joint secret without revealing anything about their secret to the attacker. One very important thing we need to be aware of here, though, is that everything we are doing is done mod p. So that means after every operation, we divide it by a large prime number p and use the remainder in the next operation. The reason for that is that it means that for every single operation here, you have no idea if the numbers that we used to create the output were larger or smaller than the output. It means that they could be sort of literally anything. And actually, that's what makes this cryptographically secure. So here I have a Typescript project set up with a hello world. But before we code the Diffie-Hellman protocol, we need to create a couple of utility functions, as well as generate our generator and base values with OpenSSL. So let's get started. First, we need some utilities to convert between primitives. Let's get going by creating a bytes to num function to convert between arbitrarily large byte arrays and big ints. Now we need a function to generate the numbers for the random private keys that we generate. So here is where we need to use Node's crypto package in order to get a cryptographically random number. Remember, it's crucial when working with cryptography to use randomness by a real cryptographic random number generator, such as Node Crypto. Now we get to the most important utility function, the modular exponent. This is the function that can raise a large exponent to a base in modulo p. We have to use really large exponents, and if we shoot over into the terminal, we can try and raise a big int to a large big int, but quickly we're going to run into an error. That's why we need this modular exponent function. So it's a function that can raise a large exponent to a base in modulo p. To do this, we use a special algorithm called the right-to-left binary method. Basically, we take the exponent, convert it to a binary number, then working from the least significant bit to the most significant bit, we can iterate over the values, squaring our total and including it in our calculation only when the current significant bit is not 0. I'll leave a link to the algorithm in the video description. Notice too that this function is a higher order function that returns a doing function to actually do the work of the exponentiation. That simplifies our API a little bit. Now we're ready to generate our parameters. So let's jump into the terminal and run these OpenSSL commands. If you're on Linux or a Mac, you most likely have OpenSSL on your system already. First, this is a command to let OpenSSL generate a huge prime number and a base for you. It takes a little while, but you get to see this pretty output display as it churns through finding huge primes. Now we have a file generated, we need to decode it by running this command. Let's copy the output to Typescript and convert it to a big int so we can work with it. Let's call it p. And we can also copy the generator value to a variable too. Let's call that g. We need to initialize our modular exponent function. Here we bind p as the modulus and return an exp function. We can use the function every time we need to do an exponent. Next, let's generate our private keys using the getRandom function, one for Alice and one for Bob. Now we can also create their public values, capital A and capital B, by raising the generator to Bob and Alice's secret values. Let's log out our public values, P, G, A and B. Lastly, let's work out their shared secrets, SA and SB, by raising Bob and Alice's public values to their opposing private counterparts. Let's log out the secrets and check that they match. Hooray, they match! You've just coded the Diffie Hellman protocol. Well, that was the Diffie Hellman protocol in pure TypeScript. So if you found this useful, give the video a thumbs up and subscribe. If you want more videos like this, we've got heaps of stuff coming up, including breaking down the entire Ethereum protocol into little bits. So stay tuned. Peace out, keep hacking.